All right, now that we've had some examples to make everything a bit more concrete, I'd like to touch base on kind of all the stuff we said about this type of problem at the start. The reason for that is because there's a lot going on, and we're only going to make it more complicated as we move forward in this section. So you really need to understand what's happening with these double integrals. So we are talking about integrating beneath some surface f of xy over some region R. And so that holds with your normal intuition that kind of here's the shape R, there's the shape R in the surface, and we kind of create the volume underneath that shape when we take these integrals. Just that intuition about what an integral is holds. And so to solve this type of integral, what you do is set up bounds for x and y to describe your region R. And you can do that in one of two ways. Oops. You can integrate with respect to x and then y. Let's compress that a little bit, sorry. Or you can integrate with respect to y and then x. And in general, you're going to do that based on what seems easiest. By whether you have more change left to right to integrate first, or whether you have more change up and down to integrate first. Remember, this is the hardest part of these problems. And you always have to make sure that your outside, your outside bounds can be written in a constant way. So if we go back to one of our examples, here's one where if we did the left version first, our up and down, we would have to break up into two pieces if we wanted to actually keep our up and down curves constant. So that one would be kind of tricky. So you pick your bounds so that the outside is constant. And those outside bounds are the furthest left, sorry, the first one is when you integrate with respect to x first, it's the lowest and highest x or y values if they're not constant. And then if you integrate with respect to y first, it's the furthest left and furthest right x values if they're not constant. So that's these examples where it looked like a curve to us, but that's because we just have to pick the furthest left and furthest right. I know I say that so many times and it probably sounds redundant, but it's so easy to forget that rule. After you set up the bounds, then solving the integral is pretty straightforward. You hold your outside variable constant to integrate with respect to your inside variable. So So for the two different paths we're on right now, first you integrate with respect to y. Integrate with respect to x, ignoring y, or integrate y, ignoring x. When you're taking your notes up and down, that'll line up with this left one and this right one are the two different approaches. And then you have to make sure your inside variable is gone. That comes when you plug in the bounds of your integral. And like a warning here, don't get rid of your outside variable. So when you all were following through the steps where I would do this thing, integrate 0 to y, well, that one's actually too easy. This one right here, I took my integral with respect to x and then plugged in numbers. Make sure that you keep all your y's. Don't plug in numbers for them. Only plug in numbers for the x's, and vice versa if you're doing the other order. Again, that's the kind of thing that I say, and it sounds silly, but when you get deep in these problems, it's really easy to forget which variable you're working with. But after you do that, you get to evaluate outside integral. And it's just a 1D problem. There's only one variable left. You know how to take integrals with respect to one variable, and then your final answer is a number. No x or y. And so that's the overall approach that we've been using in these videos, and it's the approach I described early on, but it's hard to visualize this kind of thing until you've seen some examples. So we'll get lots of practice with these integrals in your homework, and moving forward, we'll just add more and more onto them.